In this video, I would like to introduce a simple variant of gradient descent, a very simple implementation of gradient descent called coordinate descent approach. So the coordinate descent approach is very simple. It just modified only one coordinate at a time. So the method is very simple. So at each time, select just one axis among d-dimensional parameters, and then update your xt plus 1 just using the selected coordinate. So xt minus the step size gamma times the partial derivative with respect to your it's coordinate, the selected coordinate, and times the your element vectoreit. Okay, so here this indicates the partial derivative. So basically, the coordinate descent approach just compute just one single axis at a time. So that is very simple implementation of gradient descent approach. So let's consider very simple example. Let's consider this contour of your objective function. Then basically the coordinate descent approach just update one axis at a time. So update this, and then update this, and then update this, and then update this, and so on. So this approach basically not only simple but also very efficient in some case. Okay, so I'll explain why this is also efficient as well. Okay, so to understand this, I would like to introduce random coordinate descent approach. Basically, the random comes from the fact that we choose the coordinate randomly. Okay, so this is section 6.4 of Sebastian Bubeck textbook. And I will introduce a very simple form of chapter 6.4. Okay. So let's consider a very simple random coordinate descent approach where we choose the coordinate uniformly at random and then update xt plus 1 in this way. Okay, then let's assume your function f, objective function f, be a alpha strongly convex and beta smooth function. Then the random coordinate descent with step size 1 over beta. Of course, when we have beta smooth, the natural step size is 1 over beta. And with uniform sampling like this, we have this convergence speed. The expectation of fx capital T minus fx star, the optimal point, is upper bounded by 1 minus alpha over d times beta per t fx0 minus fx star. So basically the convergence speed is exponentially fast converged to 0. So let's compare this uniformly random coordinate descent approach and just pure simple vanilla gradient descent approach. When we have vanilla gradient descent approach, we have 1 minus alpha over beta per 2 capital T. So we have the additional term in the denominator, which feel like a slower convergence rate. But remember that in this case, we just compute one coordinate. Okay, so the computation time, the speed of one iteration is d times faster. Okay, so in that sense, 1 minus alpha over beta capital T roughly the same with 1 minus alpha over d beta per capital T. Okay. A more general sampling distribution than uniform is also possible. Let's consider more general case from the next slide. Okay, so coordinate-wise smooth, I want to define this one before going to more details. Okay, so basically beta smoothness means we have, if this is second derivative, we can find a second derivative element every axis, and so we can define, if we can define the Hessian of your objective function at every point, then beta smoothness means your norm of Hessian function always upper bounded by beta. Okay, that is beta smoothness definition. But in some cases, it is also possible your coordinate-wise smoothness have some different value. Okay, so your gradient with respect to one specific coordinate can have much smaller beta. Okay, so when f is beta smooth, f is also coordinate-wise smooth, and when f is alpha-strongly convex, f is also coordinate-wise alpha-strongly convex. So coordinate-wise smooth and coordinate-wise alpha-strongly convex means even if you just look at one specific axis, then your objective function also smooth and alpha-strongly convex. And this is quite a natural thing. When you have beta smooth function and when you have Hessian function, the diagonal element must be less than beta, and your diagonal element must be greater than alpha if your function is alpha strongly convex and beta smooth. And actually the diagonal term is second derivative with respect to one specific parameter. Okay, so when all the diagonal elements in between alpha and beta, which also means the coordinate-wise, your objective function f is beta smooth and alpha strongly convex. This is natural consequence from your definition, of Hessian. Okay, this is quite natural. If one of element is bigger than beta, then the norm of Hessian should be greater than beta, so we cannot say your objective function is beta smooth. Okay, so if your objective function is alpha strongly convex and beta smooth, coordinate-wise it holds as well. But reverse is not true. Okay. So f be a coordinate-wise alpha strongly convex and beta smooth function, then the random coordinate descent algorithm with gamma equal to 1 over beta and with uniform sampling has this convergence speed. Okay, which we just checked in the previous slide, right? So this is the proof. From the coordinate-wise beta smoothness, we have this. Okay, so which comes from just beta smoothness and convex property of your objective function f. And take expectation with respect to the coordinate it. Since we sample it uniformly and random, we have this inequality. And when f is alpha strongly convex, we have this inequality as well. So that was our midterm exam. And indeed, this is called Polyakrovsky condition. Okay, very hard to pronounce. So basically, this is a PL condition. So when we have alpha strongly convex, we have PL alpha condition, but the inverse is not true. If your function satisfies PL alpha condition, this does not mean always alpha strongly convex, but alpha strongly convex always imply PL alpha condition. Your norm of gradient scale always upper bound the current optimization gap fxt minus fx star with parameter alpha. Okay, so from this inequality and this inequality, we can conclude this. Okay, So usually when you have a PL condition, we have this exponentially fast conversion speed. Okay, the proof is very trivial. We did this kind of proof several times during our course. So this is very straightforward proof technique. No difficult thing. So let's extend the result to more general sampling scenario. So let f be beta I smooth for each coordinate. Okay. So now we consider different parameter beta I for each coordinate I. And let's say beta max is equal to max I beta I. Okay. Then I think the beta definitely define beta max. The previous beta is beta max. Okay. Okay, then what is the conversion speed with gamma equal to 1 over beta max with the uniform sampling? So this is the result. The result is 1 minus alpha over d times beta max power to capital T. So here beta max is equal to max of beta I. Okay, the proof just follow the previous page proof. Using this proof, we can say this conversion speed, right? Then what if we use some different learning speed, learning rate to each coordinate? So when we adaptively control the step size gamma I according to the sampled index, if your sampled index is very rapidly changed, then maybe we need to slow down the learning process. If your selected axis have very flat area, maybe we need to speed up. We need to use more larger learning rate to have better conversion speed. So this is the case. We set gamma I equal to 1 over beta I for each coordinate I. Then what is the result for convergence guarantee for this? Still, we have 1 minus alpha over t times beta max capital T. Why? From beta I smoothness of each coordinate, we have fxt plus 1 is less than or equal to fxt minus 1 over 2 beta it times gradient of it fxt square. Okay, from the beta I smoothness of each coordinate, and we set gamma I equal to 1 over beta I, we have this. Okay, but when we take expectation of fxt plus 1, since we just take it from uniformly random distribution, this is fxt minus sum of I1 to d 1 over 2 beta it d times square. Okay, so this is upper bounded by fxt minus 2 beta max gradient of fxt normed square. Okay, so in the end we still have fxt minus 1 over 2 beta max gradient of fxt normed square, and we have 1 minus alpha over d times beta max. Oh, sorry, there is d as well. D times beta max capital T conversion speed. We cannot speed up even if we use coordinate dependent running rate. Okay. But very interestingly, if we set running rate equal to 1 over beta I, so coordinate dependent running rate, and also when we sample IT not from uniformly random, but from this random distribution, and each coordinate sampled with probability beta I over sum of beta I, so proportional to the beta I parameter, then we can boost up the conversion speed. So we have the conversion speed 1 minus alpha over summation of beta I power to t. So this value, we improve the conversion speed from 1 minus alpha over d times beta max power to capital T to 1 minus alpha over summation of beta I. Okay, so why we can improve this? So the magic comes from this line. When we sample coordinate uniformly random, we just have 1 over t term here. But if we set the sample probability like this, we replace this part by 1 over 2 times summation j1 to d beta z. Okay, so which makes this part as well. 1 over 2 summation j1 to d beta z. Okay, then we can make this conversion speed. Okay, so with coordinate descent algorithm with coordinate dependent running rate and coordinate dependent sampling probability, we can basically not only make a very simple update rule, but also speed up the conversion speed. Okay. Another possible approach for coordinate descent algorithm is steepest coordinate descent approach. This is very practical, and in practice, this works very well. So basically, this algorithm simply pick the index having the steepest gradient. Okay, and then from this, basically, we can make this inequality, and then we make some nice convergence property.